I was 17 the first time I truly saw the Milky Way, not saw it on a screen or in a photograph. Actually saw it, stretched across the night sky in a way that made me feel small in a way I'd never felt before. I was on a camping trip, far enough from city lights that the entire galactic disk was visible, this luminous band of light stretching from one horizon to the other, packed with what looked like millions of stars. My friends were asleep in their tents. I was lying on my back, neck craned, just staring, and I realized something I'd known intellectually but never viscerally understood. I was looking at my home, not Earth, not the solar system, but the galaxy itself, the Milky Way, the massive rotating disk of stars and planets and dust and dark matter that contained everything I'd ever known. Billions of stars, some with planets, some with life, maybe, all part of the same galactic system as Earth. And we're just here. A tiny, insignificant dot on one of the spiral arms, orbiting a medium-sized star that nobody particularly notices, in a galaxy that itself is just one among hundreds of billions. That realization, that vertigo and wonder mixed together, is what I want to explore in this video. The Milky Way isn't just a pretty thing to look at. It's our cosmic home. It's a structure of unimaginable scale and complexity. It's been evolving for billions of years. It's headed toward a collision with another galaxy. It contains mysteries we're still discovering. And understanding the Milky Way means understanding our place in the universe. The Milky Way is a large spiral galaxy. We're inside it, which makes it hard to study, like trying to understand the structure of a forest when you're standing in the middle of the trees. It contains an estimated 100 to 400 billion stars. Let that sink in. Between 100 and 400 billion. The uncertainty exists because we can't see into dust clouds, and some regions are too far or faint. But even the lower estimate, 100 billion stars, is almost beyond comprehension. It's roughly equal to the number of galaxies we can observe in the universe. The Milky Way is roughly 100,000 light years across. A light year is the distance light travels in 1 year, about 5.9 trillion miles. So the Milky Way spans roughly 590 trillion miles. Trying to visualize that is pointless. Your brain can't grasp numbers that large. What you can grasp is scale comparison. The Earth is roughly 8,000 miles in diameter. The Sun is about 109 times larger. The distance from Earth to Sun is 93 million miles. Our solar system, everything from the Sun to the farthest comets, is roughly 2 light years across. The Milky Way is 50,000 times larger than that. Incredible. Our solar system is a tiny, insignificant speck within the Milky Way. Smaller than a speck, invisible at galactic scales. The Milky Way has a structure. It's not randomly distributed stars. It has organization. At the center is a massive bulge, a dense concentration of stars, mostly old, red stars. At the heart of this bulge is Sagittarius A star, a supermassive black hole with the mass of about 4 million suns. This black hole is the gravitational center around which the entire galaxy orbits. Surrounding the bulge is the disk, a thin, rotating structure about 1,000 light-years thick but 100,000 light-years across. This disk is where most of the galaxy's stars live. It's where we are. The disk isn't smooth. It has spiral arms, sweeping patterns of stars and gas that rotate around the galactic center. These spiral arms are where star formation is most active. They're the bright, energetic parts of the galaxy. Beyond the disk is the halo, a spherical shell of very old stars and globular clusters surrounding the disk. The halo is diffuse, not as densely packed as the disk. Throughout the galaxy is dark matter, invisible matter that provides most of the galaxy's gravitational force. We detect dark matter through its gravitational effects, but we don't know what it is. The Milky Way also contains gas and dust, the raw material for star formation. This dust is what makes the Milky Way appear to have a dark band through its middle when you look at the night sky. That dark band is dust, obscuring the light of stars behind it. Understanding the Milky Way's structure required decades of observation. For a long time, we didn't even know we were in a spiral galaxy. We thought the Milky Way might be the entire universe. In the 1920s, Edwin Hubble made observations that changed everything. He observed individual stars in nearby galaxies and measured their distances. He realized those distant, fuzzy patches weren't nebulas within our galaxy. They were entire separate galaxies, island universes far beyond the Milky Way. This was revolutionary. It transformed cosmology from thinking we were the universe to understanding we were just one galaxy among many. Since then, we've mapped the Milky Way with increasing precision. Radio telescopes let us see through dust. Infrared observations reveal stars hidden by dust clouds. Gravitational measurements let us infer the presence of dark matter. We've learned that the Milky Way isn't static. It's evolving. It's rotating. It's colliding with smaller galaxies, cannibalizing them, absorbing them into itself. Let me talk about the structure in more detail. The galactic disk is where the action is. This is where stars form, where the universe is young and active. The Sun orbits at a distance of about 26,000 light-years from the galactic center. This is about halfway out. We're in the outer regions of the disk, not at the center, not at the edge. The Sun takes about 230 million years to complete one orbit around the galactic center. We call this a galactic year or cosmic year. The last time the Sun was in this position relative to the galactic center, dinosaurs were beginning to evolve on Earth. As we orbit, we move with a velocity of about 220 kilometers per second, roughly 500,000 miles per hour. That's fast by human standards, but it's the galactic rotation speed at our distance from the center. Interestingly, this rotation speed doesn't match what we'd expect from the mass of visible stars. If only visible matter existed, objects farther from the galactic center should orbit slower, like planets in our solar system. But instead, rotation speeds stay roughly constant across the disk. This discrepancy is explained by dark matter. The galaxy is surrounded by a massive halo of dark matter, far more massive than all the visible stars combined. This dark matter provides gravitational pull that keeps the outer disk rotating as fast as the inner disk. Without dark matter, the Milky Way would fall apart. Stars in the outer disk would escape into space. The galaxy would dissolve. Instead, dark matter holds everything together. It's the invisible scaffolding that makes the galaxy's structure possible. The spiral arms are fascinating. They're not made of solid matter. They're density waves. Imagine traffic on a highway. Cars bunch up, then spread out, then bunch up again. The pattern moves along the highway even though individual cars are constantly entering and leaving the pattern. Galactic spiral arms work similarly. Stars orbit through them. Gas clouds orbit through them. The pattern rotates, creating visible spiral arms. Inside the spiral arms, gas is compressed. When gas is compressed, it can cool and collapse, forming new stars. So spiral arms are regions of active star formation. They're bright because they contain young, hot stars. The Sun is currently located between two spiral arms. We're in what's called the local arm, or Orion arm, a smaller spiral arm. This is actually fortunate. If we were inside a major spiral arm, radiation from nearby young stars would probably have prevented life from evolving on Earth. The central bulge contains mostly old red stars. These are population 2 stars, formed early in the galaxy's history from primordial gas with low heavy element content. They're metal poor by astronomical standards. The disk contains a mix of old and young stars. Young stars are hot and blue, burning through their hydrogen quickly. Old stars are cool and red, burning slowly. The Sun, at about 4.6 billion years old, is middle-aged, not young, not old. The oldest stars in the Milky Way are about 13 billion years old. The galaxy itself is about 13.6 billion years old, formed not long after the Big Bang. In the halo are globular clusters, spherical collections of hundreds of thousands or millions of stars. These clusters are ancient, containing some of the oldest stars in the galaxy. They're gravitationally bound, held together by mutual gravity rather than orbiting a common center. Globular clusters orbit the galactic center in elliptical orbits, passing through the disk periodically. Some of these clusters have been observed for centuries. They're among the brightest objects in the night sky from Earth. Now let me talk about Sagittarius A star. At the very heart of the galaxy is a supermassive black hole. We call it Sagittarius A star because it's in the direction of the constellation Sagittarius, and it's a bright radio source. The asterisk denotes a radio source designation. Sagittarius A star has the mass of about 4 million suns. It's enormous by any standard. But supermassive black holes aren't actually that big in terms of physical size. The event horizon, the point of no return, is only about 12 million kilometers across. That sounds huge until you realize it's smaller than the orbit of Mercury around our Sun. All that mass compressed into that small space creates gravitational effects that are extreme, even by cosmic standards. We know Sagittarius A star exists because we can see stars orbiting it. Astronomers have been tracking stellar orbits for decades. Some of these stars complete orbits in just a few years, moving at thousands of kilometers per second. This is only possible if there's an enormous mass at the center. In 2019, the Event Horizon Telescope, a network of radio telescopes around Earth, created the first image of a black hole. That black hole was in another galaxy, M87. But Sagittarius A star is similar, just smaller. Sagittarius A star is currently dormant. It's not actively accreting matter and radiating energy. But it could become active if a star or gas cloud got too close. Then it would become visible as an intensely luminous object, one of the brightest sources in the galaxy. Astronomers think that Sagittarius A star wasn't always dormant. Early in the galaxy's history, it was probably very active, accreting matter voraciously and radiating huge amounts of energy. This active phase shaped the galaxy's development. The gravitational influence of Sagittarius A star extends far beyond its event horizon. Stars feel its pull, orienting their orbits around it. Gas clouds spiral toward it. The black hole's presence shapes the entire structure of the central bulge. Now let me talk about the collision with Andromeda. The Milky Way isn't alone. Our nearest large galactic neighbor is Andromeda, a spiral galaxy similar in structure to the Milky Way, located about 2.5 million light-years away. Currently, Andromeda is moving toward us. It's approaching at a speed of about 110 kilometers per second. In roughly 4.5 billion years, Andromeda will collide with the Milky Way. This will be a catastrophic event, not in the sense that Earth will be destroyed, but in the sense that both galaxies will be dramatically transformed. When galaxies collide, stars don't actually hit each other. Space is too vast. Even in the densest galactic cores, the spacing between stars is enormous by human standards. The collision will instead be a gravitational interaction. The two galaxies will pull on each other, distorting their structures, sending stars careening into new orbits. The collision will unfold over hundreds of millions of years. First contact will distort both galaxies' disk structures, triggering bursts of star formation as gas clouds collide and compress. Then the galaxies will pass through each other, with orbital dynamics causing them to return for subsequent encounters. Eventually, after several passes, the two galaxies will merge into a single elliptical galaxy. This new galaxy might be called Milkomeda or Milky Andromeda. We don't know yet. The Sun will be affected. Current calculations suggest Earth's solar system will be flung into a new orbit, possibly much farther from the galactic center, possibly in a different region entirely. Some simulations show our solar system being ejected from the galaxy entirely, cast adrift in intergalactic space. But this won't happen for 4.5 billion years. By then, the Sun will have aged significantly. It will begin fusing hydrogen in its core less efficiently. Eventually, in about 5 billion years, the Sun will expand into a red giant, likely engulfing Earth. So the Milky Way Andromeda collision will occur after Earth is already dead from solar aging. But the collision will be spectacular from the perspective of any observers in other galaxies. They'll see two galaxies merge into one, a process playing out over billions of years, but still recognizable as a dramatic transformation. Let me talk about stellar populations and history. The Milky Way stars reveal its history. The oldest stars, population 2, formed from gas in the early universe. This gas was almost pure hydrogen and helium, with almost no heavy elements. These stars are now very old, having burned for over 13 billion years. The oldest are approaching the maximum age a star can reach. Eventually, they'll exhaust their hydrogen and begin to die. These old stars are found in the galactic bulge and halo. They have low heavy element abundance, confirming they formed from primordial gas. Younger stars, population 1, formed more recently from gas enriched with heavy elements. Earlier generations of stars created heavy elements through fusion and scattered them into space when they exploded as supernovae. New stars formed from this enriched gas, containing more heavy elements. The Sun is a population 1 star. It contains about 2% heavy elements by mass, elements heavier than helium. This seems small, but it's much more than the ancient population 2 stars, which contain less than 0.1% heavy elements. Heavy elements are crucial for life. Carbon, nitrogen, oxygen, silicon, iron, all the elements that make up planets and living organisms are heavy elements created in stars and scattered into space by stellar explosions. The fact that the Sun contains significant heavy elements means it must have formed from gas enriched by at least one previous generation of stars. Those earlier stars lived and died, enriching the galactic gas before the Sun formed. This is humbling. The atoms in your body were forged in stars. Not the Sun, older stars. Those stars lived billions of years ago, fused elements in their cores, exploded as supernovae, scattered those elements into space, and enriched the gas from which the Sun and solar system eventually formed. You're made of stardust, literally, elements that were fused in stellar cores billions of years ago before the sun existed. The Milky Way's star formation history can be read from the distribution of stellar ages. Young stars are concentrated in the disk, particularly in spiral arms, where active star formation is occurring. Old stars fill the bulge and halo. This pattern suggests the Milky Way's history involved initially rapid star formation in the bulge as the galaxy assembled, followed by continuous slower star formation in the disk. The recent discovery of massive young stars in the bulge suggests star formation there hasn't completely ceased, just slowed. Now let me talk about the dust and gas. The Milky Way isn't just stars, it's also filled with gas and dust. Interstellar dust is tiny particles, mostly silicates and carbon compounds, ranging from micrometers to millimeters in size. These particles are created in stellar atmospheres and scattered into space. They accumulate in clouds between stars. Dust is what makes the Milky Way appear to have a dark band through the middle when viewed from Earth. That dark band is dust obscuring starlight from more distant stars. Dust plays a crucial role in star formation. When gas and dust clouds collapse under their own gravity, dust particles help cool the gas by radiating away energy. This cooling allows the cloud to collapse into a compact object that can ignite fusion, a star. Interstellar gas is mostly hydrogen, with some helium and trace amounts of heavier elements. This gas exists in different states: hot ionized gas near young stars, cool molecular clouds forming new stars, diffuse atomic gas in the interstellar medium. Gas clouds in spiral arms are compressed by the passage of the spiral density wave. This compression triggers star formation. The stars that form from a gas cloud's collapse eventually release energy that heats the gas and disperses it. The cleared region becomes a cavity, an H2 region, an area of ionized hydrogen around young stars. This cycle, compression triggering star formation clearing regions, clearing preventing further star formation until more compression occurs, gives the galaxy its spiral structure and dynamics. The total mass of gas in the Milky Way is roughly equal to the mass of all stars. This means there's enough raw material for roughly as much star formation in the future as has already occurred. How much longer will the Milky Way continue forming stars? Billions of years, probably. But eventually, as gas is converted to stars and stars end their lives, returning mass to the interstellar medium in new forms: white dwarfs, neutron stars, black holes, escaped stellar winds, star formation will slow and eventually cease. In the far distant future, trillions of years from now, the Milky Way will contain mostly dead stellar remnants, with essentially no new stars forming. Let me talk about what we've learned from observations. For most of human history, the Milky Way was just a bright band of light in the night sky. People didn't know what it was. In the 1600s, Galileo pointed his telescope at it and discovered it was made of countless stars. But the true scale and structure remained unknown. In the early 1900s, astronomers realized the Milky Way had a structure, more stars in one direction than another, suggesting a disc-like shape. But they still didn't know the full extent. Edwin Hubble's work in the 1920s revealed other galaxies existed beyond the Milky Way. This transformed understanding of the galaxy's significance. It was large, but not the entire universe. Over the 20th century, various observations revealed the spiral structure, the central bulge, the disk, and eventually the halo and dark matter. In the 1970s, Vera Rubin's observations of galaxy rotation curves provided strong evidence for dark matter. galaxies rotated too fast to be held together by visible matter alone. Dark matter was required. In recent decades, radio and infrared observations have mapped the Milky Way with increasing precision. The Gaia satellite, launched by the European Space Agency, has measured the positions and motions of over 1 billion stars, creating the most detailed map of the galaxy yet. These observations revealed the spiral structure, confirmed the presence of multiple satellite galaxies orbiting the Milky Way, detected stellar streams, evidence of galaxies being torn apart and absorbed by the Milky Way's gravity. We've also detected massive black holes in the bulge beside Sagittarius A star, discovered thousands of exoplanets in the galaxy, and identified regions of intense star formation hidden in dust clouds. Modern observations are revealing the Milky Way to be far more dynamic and complex than we imagined. It's a living, evolving structure, not a static artifact. Now let me talk about satellite galaxies and cannibalism. The Milky Way isn't growing alone. It's surrounded by smaller galaxies, satellite galaxies, orbiting it gravitationally. The largest satellite galaxies are the Large and Small Magellanic Clouds. They orbit the Milky Way and they're being gradually torn apart by tidal forces. In the future, they'll be completely absorbed into the Milky Way. This is actually how galaxies grow. Large galaxies cannibalize smaller ones. The Milky Way has likely absorbed dozens of smaller galaxies over its history. Evidence for this includes stellar streams, long, thin trails of stars orbiting the Milky Way that are remnants of disrupted satellite galaxies. We've detected dozens of these streams, evidence that the Milky Way is actively consuming nearby galaxies. This process explains part of why the Milky Way is so large. It's grown not just through star formation, but through galactic mergers. Andromeda is also cannibalizing satellite galaxies. When Andromeda collides with the Milky Way, both will have grown from consuming smaller galaxies, making the merger more dramatic. The future galaxy formed from the Milky Way Andromeda merger will be even larger, having consumed both spiral galaxies and all their satellites. Let me talk about visibility and observation from Earth. From Earth, the Milky Way is visible as a bright band across the night sky. In truly dark locations, far from city lights, it's spectacular. In cities, light pollution washes it out completely. The visible band is the disk of the galaxy seen edge-on. The densest part is in the direction of Sagittarius, where we're looking toward the galactic center. The brightest parts of the Milky Way visible from Earth include Sagittarius, toward the galactic center, Cygnus, in the northern sky, Cassiopeia, northern sky, Crux, southern sky, Centaurus, southern sky. These bright regions mark where we're looking through the disk toward dense star fields or where spiral arms contain particularly bright young stars. The dark band along the Milky Way marks where dust obscures starlight. With telescopes, we can resolve individual stars. With radio telescopes, we can see through dust to regions hidden in visible light. With infrared telescopes, we can detect young stars embedded in dust clouds. Modern surveys have cataloged hundreds of millions of stars. Gaia has provided precise three-dimensional positions and velocities for over 1 billion stars, creating a detailed map of the galaxy's structure. From these observations, we've learned that the Milky Way is warped. The outer disk isn't flat, but bends upward and downward. This warping is likely caused by gravitational interactions with satellite galaxies. We've learned that the spiral arms aren't stationary features, but evolving structures. The pattern rotates, and stellar populations flow through the arms over billions of years. We've learned that the galaxy is more complex and dynamic than static models suggested. Let me talk about star formation regions. The Milky Way hosts numerous regions of active star formation. These are primarily in the spiral arms, where gas is compressed and conditions favor the collapse of gas clouds into stars. Some famous star-forming regions visible from Earth include the Orion Nebula, a region where baby stars are emerging from dust clouds; the Crab Nebula, remnant of a supernova observed by Chinese astronomers in 1054 AD; the Eagle Nebula, site of intense star formation; the Eta Carinae Nebula, surrounding one of the most massive stars known. These regions are spectacular to observe. Young stars embedded in dust clouds ionize the surrounding gas, creating glowing nebulae. Stellar winds and radiation shape the gas into intricate structures. Star formation regions are where the galaxy's future is being born. New stars will take billions of years to live, fusing hydrogen, creating heavy elements, eventually dying and returning those elements to the interstellar medium. Some of these newly forming stars will have planets. Some of those planets might develop life. The processes happening in star-forming regions today will determine what kinds of civilizations might exist in the galaxy billions of years from now. Let me talk about exotic objects. The Milky Way contains not just stars, but also more exotic objects. Neutron stars are created when massive stars explode as supernovae. The core collapses to such density that protons and electrons merge into neutrons. A teaspoon of neutron star material would weigh as much as all the ships ever built. Neutron stars can rotate extremely fast, hundreds of times per second. As they rotate, they emit radiation like a lighthouse, creating pulsars, precisely periodic signals we can detect from Earth. Black holes form when the most massive stars die. The core collapses completely, creating a region where gravity is so strong nothing escapes, not even light. Stellar black holes, 10 to 20 solar masses, are scattered throughout the disk. Some are in binary systems with companion stars, accreting matter and emitting X-rays detectable from Earth. Supermassive black holes like Sagittarius A star exist in galactic centers, but are less common than stellar black holes. White dwarfs are the dense remnants left after low-mass stars like the Sun die. They're about the size of Earth, but with the mass of the Sun. They gradually cool over billions of years. Brown dwarfs are objects that failed to become stars. They accumulated enough mass to heat up, but not enough to ignite hydrogen fusion. They're planets or failed stars, depending on your perspective. The Milky Way contains billions of black holes, neutron stars, white dwarfs, and brown dwarfs, most invisible to our telescopes, but inferring their presence through gravitational effects on visible objects. Now let me talk about the future. The Milky Way's future is shaped by its past and present dynamics. Star formation will continue for billions of years, but will gradually slow as gas is consumed by star formation and stellar processes. Eventually, the collision with Andromeda will occur, transforming both galaxies into a single elliptical galaxy. In the far distant future, trillions of years from now, stars will exhaust their fuel. Stellar remnants will dominate. The galaxy will contain mostly white dwarfs, neutron stars, and black holes. Eventually, over even longer timescales, stellar remnants will evaporate or fall into central black holes. The galaxy will fade into a diffuse collection of faint objects scattered through space. This is the far future. But it's written in the physics governing stellar evolution and galactic dynamics. the Milky Way will eventually die, like all galaxies. But that's billions or trillions of years away. For the foreseeable future, the Milky Way will remain a dynamic, evolving system, birthplace of new stars and worlds. And we, here on Earth, orbiting a medium-sized star in an outer spiral arm, are products of that system. We're made of atoms forged in ancient stars. We live on a planet orbiting one of billions of stars. We'll eventually die, and our atoms will return to the galactic medium, potentially becoming part of new stars, new planets, new life. Let me go deeper into the Milky Way structure because understanding how it's organized helps you grasp its scale and complexity. The galactic disk is the most visible component. It's the plane where most stars exist. Think of it as a flat circular pancake about 1,000 light years thick, but 100,000 light years across. This disk isn't uniform. The stellar density increases toward the galactic center, peaks in the bulge, then decreases as you move outward. The surface brightness of the disk, how many photons per unit area reach you from a given direction, roughly follows an exponential decline with distance from the galactic center. This mathematical relationship tells us something about how the Milky Way formed. Exponential profiles often emerge from systems that evolved from a concentrated center and expanded outward over time. The disk contains stars of all ages, but younger stars tend to concentrate more strongly toward the spiral arms, while older stars are more uniformly distributed. This suggests the spiral arms contain recently formed stars, while older stars have had time to dispersing throughout the disk. The galactic bulge is a dense concentration of stars at the center, extending about 5,000 light years from the galactic center. It's not spherical, it's boxy or peanut-shaped, which is thought to result from bar-like dynamics in the galaxy's center. Yes, the Milky Way might have a central bar, an elongated structure in the bulge that rotates. Evidence for this includes the offset between the galactic center and the densest part of the bulge, suggesting an asymmetric structure. If the Milky Way does have a central bar, it affects stellar dynamics. Stars in the bar experience different gravitational forces than they would in a purely spherical bulge. This can trigger orbital resonances that cause stars to move in particular patterns. The galactic halo extends out to roughly 300,000 light years from the galactic center. It's sparsely populated, much less dense than the disk, but it extends much farther. The halo contains mostly old stars and globular clusters. It might also contain a dark matter halo, which many theorists believe extends even farther, perhaps to 1,000,000 light years or more. The dark matter halo is invisible, but its gravity shapes the galaxy. Without it, the outer disk would rotate too fast and escape into space. The spiral arms are among the Milky Way's most dramatic features, and they're not what they appear to be. When you look at images of spiral galaxies, the spiral arms appear to be made of stars. But that's not quite right. The spiral arms are density waves, patterns that rotate around the galactic center at a fixed pattern speed. Imagine traffic on a highway. Even though individual cars keep moving, the pattern of congestion seems to stay in place or even move backward while the cars move forward. Galactic spiral arms work similarly. Individual stars orbit through the pattern, but the pattern itself persists. Why is this important? Because it means the spiral arms aren't physical structures that would tear apart over time if they were made of the same stars. Instead, they're waves, regions where density is temporarily higher. Stars, gas, and dust pass through them like vehicles passing through a traffic jam. Inside the spiral arms, gas clouds are compressed. The compression can trigger gravitational instability, causing clouds to collapse into stars. That's why spiral arms are regions of active star formation. The compression is also where dust is concentrated, making spiral arms dusty. This dust blocks starlight from more distant objects, making spiral arms appear darker in visible light despite containing young, hot stars. The Milky Way probably has a four-armed spiral structure, though some observations suggest additional minor arms. The spiral pattern rotates at a speed different from individual stellar orbits, which creates a corotation radius, where the pattern speed matches stellar orbital speed. Our solar system is currently outside the major spiral arms in the local arm, a minor arm between two major arms. This is actually fortunate for the development of life on Earth. Major spiral arms contain many young, massive stars that emit intense radiation. Constant exposure to such radiation would have made Earth's surface hostile to life for most of its history. By being between spiral arms, Earth has been in a relatively quiet region, free from the harsh radiation environment inside major arms. One of the most profound mysteries revealed by Milky Way observations is the rotation curve problem, and it led to the discovery of dark matter. When astronomers measure the orbital velocities of stars at different distances from the galactic center, they expect to find that outer stars move slower than inner stars, similar to how planets in our solar system orbit slower the farther they are from the sun. This expectation comes from gravity. If gravity follows an inverse square law, and if most of the galaxy's mass is concentrated toward the center, then outer regions should have lower orbital velocities. But observations show something strange. Stars in the outer disk orbit at roughly the same velocity as stars closer to the center. The rotation curve is flat. For decades, this was puzzling. The outer stars were moving too fast to remain in orbit around only the visible mass. They should escape into space. The solution came from reconsidering what mass actually exists. If the rotation curve is flat, then mass must be distributed differently than visible stars suggest. Specifically, mass must extend much farther out than visible stars. This led to the dark matter hypothesis. Invisible matter, not stars, gas, or dust, makes up most of the galaxy's mass. This dark matter extends in a halo around the galaxy, providing the gravitational force needed to keep outer stars in orbit. The evidence for dark matter is compelling and comes from multiple sources. Rotation curves, flat instead of declining, satellite galaxy orbits, they move too fast to stay orbiting with visible mass alone, X-ray emissions, hot gas in clusters of galaxies moves too fast, gravitational lensing, bending of light around massive structures, cosmic microwave background observations, patterns in radiation require dark matter. We estimate that about 85% of the matter in the universe is dark matter. Only 15% is ordinary matter, atoms and molecules and light. For the Milky Way specifically, dark matter makes up about 90% of the total mass. The galaxy's gravitational effects are dominated by invisible matter we don't understand. What is dark matter? We don't know. The leading candidate is WIMPs, weakly interacting massive particles. Hypothetical particles that barely interact with ordinary matter except through gravity. Other candidates include axions, ultralight particles, and primordial black holes. Black holes formed in the early universe rather than from stellar collapse. Experiments are actively searching for dark matter particles, but so far they've eluded detection. Dark matter remains one of physics' greatest mysteries. For the Milky Way, dark matter's existence is certain. Its composition remains unknown. Observing the Milky Way is challenging because we're inside it. We're trying to map the structure of a disk-shaped galaxy from a point within the disk, obscured by dust and gas. Nevertheless, astronomers have developed clever techniques to pierce through the dust and map the galaxy. Parallax measurements were the first method. When you look at a nearby star from opposite sides of Earth's orbit around the Sun, the star appears to shift position against distant background stars. This parallax shift allows us to measure the star's distance. Hipparcos, a satellite launched in 1989, measured parallaxes for nearly 120,000 stars, creating the first precise distance map of nearby stars. This data revealed the structure of the local stellar neighborhood and allowed us to calibrate other distance measurement techniques. Gaia, launched in 2013, improved dramatically on Hipparcos. It has measured precise positions and parallaxes for over 1 billion stars, plus their velocities. This has created an unprecedented three-dimensional map of the Milky Way. Gaia data revealed that the galactic disk is warped, not flat, but bending upward and downward at larger distances from the galactic center. This warping is likely caused by gravitational interactions with satellite galaxies. Amazing. Gaia also revealed stellar streams, thin filaments of stars tracing out paths through the galaxy. These streams are debris from satellite galaxies being torn apart by tidal forces from the Milky Way. Photometric methods estimate distances by measuring apparent brightness and assuming intrinsic brightness. Different types of stars have different intrinsic brightness, so measuring spectral type and apparent magnitude allows distance estimation. This technique is less precise than parallax, but works for more distant objects where parallax becomes too small to measure. Spectroscopy reveals stellar velocities through the Doppler shift of spectral lines. Gas or stars moving toward us show blue shifted light. Objects moving away show red shifted light. By measuring the shift, we can determine line of sight velocity. Combining spectroscopic velocity with proper motion, positional change over time from parallax or proper motion surveys gives us complete three-dimensional motion of stars. Radio observations penetrate dust clouds' opaque, invisible light. Neutral hydrogen emits radiation at 1.4 gigahertz frequency, allowing radio telescopes to map hydrogen gas distribution throughout the galaxy even in dust-obscured regions. Radio observations revealed the spiral structure, confirmed the galactic bar, and traced gas kinematics. Infrared observations similarly penetrate dust by observing radiation that dust is transparent to. Infrared telescopes reveal young stars embedded in dust clouds and the galactic center hidden behind dust. The Spitzer Space Telescope and other infrared observatories have mapped star formation throughout the galaxy, revealing regions of active star birth hidden in dust. X-ray observations detect hot gas and exotic objects like neutron stars and black holes. X-ray observatories like Chandra reveal the hot interstellar medium, supernova remnants, and accretion around compact objects. Ultraviolet observations are absorbed by Earth's atmosphere, so they require space telescopes. UV light reveals hot, young stars and ionized gas heated by stellar radiation. Combining observations across the electromagnetic spectrum, radio, infrared, visible, ultraviolet, X-ray, gamma ray, gives us a complete picture of the Milky Way in all its complexity. The Sun doesn't exist in isolation. It's surrounded by other stars, the stellar neighborhood that defines our local galactic context. The nearest star to the Sun is Proxima Centauri, about 4.24 light years away. It's a red dwarf, a small, cool star that's inherently faint. The reason we know it's closest is because astronomers measured its parallax, the tiny shift in position as Earth orbits the Sun. Beyond Proxima Centauri, the next nearest stars are Alpha Centauri A and B, a binary system about 4.37 light years away. Alpha Centauri A is similar to our Sun, a yellow dwarf. Alpha Centauri B is an orange dwarf. Both Alpha Centauri A and B might have planets. In 2016, astronomers detected a planet around Proxima Centauri. This is significant because it shows planets can exist even around small nearby stars. Wow. Within 10 light years of the Sun, there are about 50 known stars. Within 20 light years, there are hundreds. These nearby stars define the local neighborhood of the Milky Way. Most nearby stars are red dwarfs, small, cool, dim stars that burn their fuel slowly, potentially lasting hundreds of billions of years. Because red dwarfs are so numerous, they're the dominant stellar type in the Milky Way, though they're often too dim to see without telescopes. A few nearby stars are more massive and brighter than the Sun. Sirius, about 8.6 light years away, is the brightest star in Earth's night sky. It's actually a binary system. Sirius A is a blue-white star, more massive and luminous than the Sun, while Sirius B is a white dwarf, the dense remnant of a dead star. The presence of a white dwarf in the Sirius system tells us that Sirius A's companion once was more massive, lived its life, expanded into a red giant, shed its outer layers, and left behind the white dwarf remnant. This is evidence of stellar evolution and the fate of massive stars. Most nearby stars are moving in roughly the same direction as the Sun, orbiting the galactic center together. This defines the local standard of rest, an average motion of stars in the solar neighborhood. The Sun itself moves at about 220 kilometers per second around the galactic center, but it also has its own motion relative to nearby stars. This motion through the local stellar neighborhood will eventually take the Sun closer to or farther from other stars. In about 10,000 years, a star called Gliese 710 might pass within 1.6 light years of the Sun. At this distance, its gravity would perturb the outer solar system, potentially destabilizing some cometary orbits. This demonstrates that the Sun isn't stationary. It's in constant motion relative to other stars. Over millions of years, the solar neighborhood's composition will change as stars drift into and out of the local region. The Sun was born elsewhere in the Milky Way and migrated to its current location over its 4.6 billion year lifetime. We don't know precisely where the Sun was born. There are several hypotheses based on chemical abundance patterns and orbital dynamics, but it was definitely elsewhere when it formed. Before 1995, we had never confirmed the existence of a planet orbiting another star. Astronomers suspected planets should exist. The formation process that created our solar system should occur elsewhere, but direct evidence was lacking. In 1995, astronomers detected the first exoplanet orbiting a Sun-like star called 51 Pegasi. The detection method was Doppler spectroscopy, measuring the star's motion caused by the planet's gravity. Since then, we've discovered over 5,000 exoplanets, and the rate of discovery accelerates as our detection methods improve. Exoplanet discoveries have revealed that planetary systems are ubiquitous. Planets probably form around most stars. Some stars have multiple planets. Some planets orbit unusual stars, white dwarfs, neutron stars, even black holes, theoretically. The diversity of planetary systems is astonishing. Some have planets orbiting incredibly close to their stars, hot Jupiters with orbital periods of just a few days, with surface temperatures exceeding 1000 Kelvin. Others have planets in wide orbits, far from their stars. Some have planets in unusual orbital resonances where the planetary orbital periods have simple ratios, 3 to 1, 2 to 1, etc., suggesting gravitational dynamics or formation processes we don't fully understand. Some planetary systems are tightly packed with multiple planets in close orbits. Others are sparse with planets far apart. The diversity suggests different formation and evolution processes. Of particular interest are planets in habitable zones, regions where liquid water could exist on a planet's surface. Such planets might harbor life. Habitable zone calculations consider the star's temperature and luminosity. For a given star, the habitable zone is the orbital distance range where a planet receiving neither too much nor too little stellar energy could maintain liquid water. Earth orbits in the Sun's habitable zone. So do Venus and Mars, though Venus is too hot and Mars too cold for liquid water to remain stable, though Mars had liquid water in its past. Many exoplanet discoveries include planets in habitable zones. In 2015, the Kepler Space Telescope discovered Kepler 452b, an Earth-sized planet orbiting a Sun-like star in its habitable zone. It became known as Earth's cousin. Not all habitable zone planets would actually harbor life. A habitable zone is just the region where conditions are right for liquid water. Many other factors affect habitability: presence of a protective magnetic field, atmospheric composition, plate tectonics, protection from stellar radiation, and others. Still, the abundance of potentially habitable planets in the Milky Way is striking. If billions of such planets exist, and even a tiny fraction harbor life, the galaxy could be teeming with biology. This connects to one of astronomy's greatest mysteries, the Fermi paradox. The Fermi paradox notes that if the galaxy likely contains billions of planets, and many might harbor advanced civilizations, where are the aliens? Why haven't we detected signals from extraterrestrial intelligences? Several explanations are possible. Perhaps life is rarer than we think. Perhaps civilizations typically destroy themselves before developing interstellar communication. Perhaps advanced civilizations exist but don't broadcast signals we'd recognize. Perhaps we're living in an unusually quiet region of the galaxy. Or perhaps the Great Filter, some barrier preventing civilizations from expanding galaxy-wide, exists in our past. We're lucky to exist, or our future. Something will destroy our civilization. The Search for Extraterrestrial Intelligence, SETI, uses radio telescopes to listen for signals from other civilizations. So far, no confirmed signals have been detected, though some anomalies have generated excitement before being explained as natural phenomena or instruments artifacts. The Breakthrough Listen initiative, launched in 2015, is conducting the most comprehensive SETI search to date, examining 1 million stars for signals from advanced civilizations. Whether we discover signals or not, the abundance of planetary systems in the Milky Way suggests we're not alone in the universe. The question is whether any of those distant civilizations are currently broadcasting, or whether the galaxy's history of life has been quieter than we optimistically assume. Surrounding our solar system is a region called the local bubble, a low-density cavity in the interstellar medium about 300 light-years across. Inside the local bubble, The density of interstellar gas is lower than in surrounding regions. This low density might result from supernovae explosions that evacuated material from the region, or it might reflect the natural distribution of gas in our region of the galaxy. The local bubble contains our Sun and several nearby stars. It's bounded by higher density gas, including clouds and filaments that mark the edges of the bubble. The Sun is currently moving through the local bubble, passing through regions of denser and less dense gas as it orbits the galactic center. Earth's climate has probably been affected by the density of interstellar material surrounding the solar system. Denser gas provides more shielding from cosmic rays, while less dense gas allows more cosmic rays to reach Earth. Cosmic rays are high-energy particles originating from space. Most come from supernovae, stellar explosions that accelerate particles to extreme energies. Some cosmic rays reach Earth's atmosphere, creating secondary particles that reach the surface. The flux of cosmic rays reaching Earth depends on the interstellar medium density, the Sun's magnetic field, Earth's magnetic field, and solar activity. Variations in cosmic ray flux have been proposed to affect cloud formation and potentially climate, though this connection remains debated. The interstellar medium itself is complex, consisting of different phases. Hot ionized gas at temperatures above 1,000,000 Kelvin, created by stellar explosions and intense radiation. Warm ionized gas at thousands of Kelvin around hot stars. Neutral atomic gas at hundreds of Kelvin. Molecular gas in clouds at tens of Kelvin where stars form. Dust grains of silicates and carbon in clouds. These different phases are in dynamic equilibrium. Energy flowing in and out, gas heating and cooling, clouds forming and dispersing. The magnetic field of the Milky Way also plays a role. Magnetic fields permeate the galaxy, threading through gas clouds and interstellar space. These fields influence gas dynamics, guide cosmic rays, and affect stellar formation. Measurements of magnetic field strength throughout the galaxy show the field is complex, with orientations that vary with position. Near the galactic plane, the field is roughly parallel to the plane. In the galactic halo, the field is more tangled. The total energy density of the magnetic field is comparable to the energy density of cosmic rays and radiation, making it dynamically important to galactic processes. Stars in the galaxy don't orbit in perfect circles. They follow elliptical orbits that bring them closer to and farther from the galactic center as they complete their 230 million year galactic years. These orbits are shaped by the gravitational potential of the galaxy, the collective gravity of all stars, gas, and dark matter. The solar system's orbit is eccentric, meaning our distance from the galactic center varies. The Sun is currently about 26,000 light years from the center. Its orbit brings it as close as about 23,000 light years and as far as about 29,000 light years. This orbital variation might affect Earth's climate. When the solar system is closer to the galactic center, it's immersed in denser gas and exposed to more cosmic rays. This could trigger ice ages through reduced solar input. More cosmic rays increase cloud formation, blocking sunlight. Some researchers have suggested that mass extinction events on Earth correlate with the solar system's position in its galactic orbit, though this connection remains speculative. Stars also move perpendicular to the galactic plane, oscillating up and down as they orbit. The Sun completes these vertical oscillations about 2.5 times per galactic year. Currently, the Sun is moving toward the galactic plane. The oscillation period of about 100 million years has been suggested as a possible cause of extinction pulses on Earth. But again, this is debated and not conclusively established. Stars also have random motions relative to the galactic plane, velocity dispersions that represent random kinetic energy. Older stellar populations have higher velocity dispersions, suggesting they've been scattered over billions of years by gravitational interactions. Younger stars have lower velocity dispersions, indicating they were born from gas clouds that had relatively organized motion. The velocity dispersion of stars increases with age because gravitational encounters and disk heating gradually increase random motions. This is one way astronomers determine stellar ages. Old stars move more randomly relative to the galactic plane than young stars. Globular clusters also have their own motions. Their orbits can bring them through the galactic disk, where they might interact with gas clouds or other structures. Some globular clusters have been detected in the process of being disrupted by tidal forces from the galaxy, their stars being pulled away to form stellar streams. The dynamics of the galaxy are complex and chaotic at some level. Small changes in initial conditions can lead to wildly different outcomes over billions of years. Despite this deterministic chaos, statistical patterns emerge. The overall structure persists even if individual stellar orbits become unpredictable. The Milky Way's stars contain a record of the galaxy's chemical evolution, how the abundance of heavy elements has changed over time. Early in the galaxy's history, only hydrogen and helium existed. The first stars formed from this pristine gas, containing no heavy elements. When these early stars died, they created heavy elements through fusion and scattered them into space through supernova explosions. Subsequent star formation occurred from gas enriched with these newly created elements. Each generation of stars increased the heavy element abundance in the interstellar medium. This is why we classify stars by metallicity, the fraction of heavy elements in their composition. Population 2 stars, old, bulge, and halo stars, have low metallicity. They contain less than 0.1% heavy elements by mass. Population 1 stars, younger, disk stars, have higher metallicity. The Sun, at about 2% heavy elements, is typical of intermediate age population 1 stars. The most metal-rich stars in the disk are very young, formed recently from gas enriched by billions of years of stellar nucleosynthesis. The metallicity gradient throughout the galaxy shows a pattern. Stars near the galactic center are more metal-rich than stars in the outer disk. This gradient formed because star formation was most intense in the center early in galactic history, rapidly enriching that region with heavy elements. The outer disk enriched more slowly, so stars there are metal poorer. This metallicity gradient allows us to study galactic chemical evolution. By measuring metallicities of stars at different galactic locations and ages, we can infer how chemical abundances evolved throughout the galaxy. The distribution of specific elements, carbon, nitrogen, oxygen, iron, also tells us about nucleosynthesis processes. Elements created in different ways, core fusion in massive stars, explosive nucleosynthesis, neutron capture processes, have different signatures. By analyzing the abundance ratios of elements in stars, astronomers can determine which nucleosynthesis processes contributed to creating that star's composition. The alpha elements, oxygen, neon, magnesium, silicon, sulfur, argon, created primarily in massive star explosions, show particular abundance patterns. Stars with high alpha element abundances formed from gas enriched primarily by massive star explosions. This reveals that the old, metal-poor stars formed when massive stars dominated the stellar population, while younger stars formed later when lower mass stars began significantly contributing. The Milky Way's chemical evolution is still ongoing. Each new generation of stars increases the heavy element abundance slightly, given billions of years remaining before the galaxy merges with Andromeda. Heavy element abundances will increase substantially. In the far future, after the merger, the combined galaxy would eventually contain stars with even higher metallicities than the current maximum, if star formation continued long enough. Supernovae are the primary mechanism by which the Milky Way enriches itself with heavy elements. When a massive star, more than 8 solar masses, reaches the end of its life, its core collapses catastrophically and rebounds in a supernova explosion. This explosion disperses the star's material throughout the galaxy at velocities of 10,000 to 30,000 kilometers per second. The explosion creates heavy elements, iron, nickel, cobalt, through nuclear fusion in the shock wave. These newly created elements are scattered into surrounding gas clouds. Type 1, A supernovae, which occur in binary systems where a white dwarf accretes material from a companion star, also contribute significantly to galactic enrichment. They create large amounts of iron and nickel. The explosion of a single supernova can energize a huge volume of gas. A supernova remnant expands through the interstellar medium, pushing gas outward, heating it, and creating cavities like the one containing our solar system. Multiple supernovas in the same region create larger cavities, superbubbles, that can expand to hundreds of light years across. Star-forming regions produce many massive stars, which explode as supernovae in quick succession. Massive stars live only millions of years. A concentrated burst of supernovae can heat gas dramatically, disrupting star formation and clearing the region. This self-regulating cycle, star formation producing massive stars, supernovae disrupting star formation, controls how efficiently galaxies form stars. Without supernovae feedback, galaxies would convert nearly all their gas into stars quickly, forming far fewer galaxies with more stars than we observe. Supernova feedback limits galaxy growth. Supernova remnants are visible as diffuse nebulae glowing in the light of radiation from shocked gas. The Crab Nebula, remnant of a supernova observed in 1054 AD by Chinese astronomers, is one of the most famous examples visible from Earth. Supernova remnants also contain exotic objects, neutron stars and black holes left behind after the explosion. Pulsars, rotating neutron stars, have been discovered in some remnants. The cosmic abundance of elements reflects the history of supernova explosions. Elements created in supernova have characteristic abundance ratios determined by explosive nucleosynthesis calculations. By analyzing the abundances of elements in meteorites and stars, we can infer the history of supernova explosions that contributed to creating those compositions. Some iron in your blood, some calcium in your bones, some carbon in your proteins, all were created in supernova explosions long before the solar system formed. Think about it. Globular clusters are among the most beautiful objects in the night sky, dense spherical collections of hundreds of thousands to millions of stars. These clusters are ancient, containing some of the oldest stars in the Milky Way. Stars in globular clusters can be 13 billion years old, formed very early in galactic history. Globular clusters are nearly metal-free, containing less than a few percent of the sun's heavy element abundance. This confirms they formed early, before the galaxy had enriched itself with heavy elements. About 150 globular clusters orbit the Milky Way. They're spread throughout the halo, but some have orbits bringing them through the disk. Very cool. Each globular cluster contains hundreds of thousands to millions of stars packed into a region just tens of light years across. The stellar density in cluster cores is so high that stars are separated by just a few light days. This creates an environment completely unlike the galactic disk. Stars and globular clusters can interact gravitationally, scattering each other into new orbits. Close encounters are relatively common. In such an environment, planet formation is probably rare. Any planets forming would likely be ejected by close stellar encounters, so globular clusters probably host few planets. But globular clusters are spectacular laboratories for Sake is studying stellar evolution. With so many stars of different ages, though all very old, globular clusters show stellar evolution in action. The Hertzsprung-Russell diagram, a plot of stellar luminosity versus color, reveals the evolutionary path of stars. Globular clusters show a clear pattern. Some stars have evolved off the main sequence, single hydrogen burning phase, and become red giants. By comparing the brightness of the brightest stars in a globular cluster to theoretical models of stellar evolution, we can determine the cluster's age. Globular clusters also contain exotic objects. Some have black holes, detected through the kinematics of surrounding stars. Some have pulsars, neutron stars spinning hundreds of times per second. Some globular clusters contain blue stragglers, apparently young, hot, blue stars in a cluster of old stars. These are thought to form through stellar mergers or mass transfer in binary systems, restarting fusion and making the star appear younger than its actual age. Globular clusters are slowly evaporating. Stars on the cluster's outer edges occasionally escape the gravitational pull of the cluster and drift off into the galaxy. Over billions of years, globular clusters lose stars this way. Some clusters are being actively disrupted. Tidal forces from the galaxy's gravity are pulling them apart, stretching them into streams of stars. The Sagittarius Dwarf Elliptical Galaxy, a small satellite galaxy of the Milky Way, is currently being torn apart by tidal forces. Its remnants form a stream of stars wrapping around the Milky Way multiple times. This is the fate of all satellite galaxies eventually. The Milky Way's gravity will continue cannibalizing smaller galaxies, absorbing their stars, leaving trails of stellar streams as evidence of destruction. The galactic center is one of the most extreme environments in the Milky Way. Sagittarius A star, the supermassive black hole at the center, creates a gravitational environment unlike anywhere else in the galaxy. Stars orbit it at velocities reaching thousands of kilometers per second, completing orbits in just a few years. The region within a light year of Sagittarius A star is crowded with stars. The stellar density there is 1,000,000 times higher than in Earth's solar neighborhood. Despite this crowding, stars still don't collide because space is vast, even at galactic center scales. But close encounters are common, and stars' orbits are frequently perturbed. Some stars, called S stars, have been observed completing orbits around Sagittarius A star. Their orbital parameters, size, eccentricity, period, are precisely measured by decades of patient observation. From these orbits, astronomers calculated Sagittarius A star's mass, about 4.1 million solar masses. In 2019 and 2020, the Event Horizon Telescope captured images of another supermassive black hole in the galaxy M87. These were the first direct images of black hole event horizons, confirming Einstein's predictions about black hole physics. Sagittarius A star is smaller and less luminous than the M87 black hole, making it harder to image. But similar radio observations are ongoing, and we might soon have a direct image of Sagittarius A star itself. The region around Sagittarius A star is also a source of energetic phenomena. Periodic flares of radiation suggest material is orbiting close to the black hole, occasionally falling in and releasing enormous energy. Jets of materials sometimes emanate from the galactic center, visible in radio observations as structures extending thousands of light years. The gravitational tidal forces near Sagittarius A star are intense. An object would be spaghettified, stretched to thin strands, by differential gravity before crossing the event horizon. If a star ventured too close, a star's gravity might tear it apart. The remnants would form an accretion disk, spiraling inward and releasing tremendous radiation before being consumed by the black hole. Several star-tearing events have been observed in other galaxies, producing bright outbursts that fade as the disrupted star's material is consumed. The galactic center also contains a massive stellar cluster, the central cluster, with millions of stars within a few light years of Sagittarius, a star. This dense stellar environment is unlike anywhere else in the Milky Way. The density is so high that thousands of stars would be visible to the naked eye if we stood there, creating a sky orders of magnitude brighter than from Earth. The Milky Way is large, but not the largest galaxy known. The largest galaxy discovered so far is C1101, an elliptical galaxy containing an estimated 100 trillion stars, roughly 1,000 times more than the Milky Way. But IC1101 is an outlier, formed through numerous galactic collisions and mergers. Most large galaxies contain fewer stars than the Milky Way. Andromeda, our nearest large galactic neighbor, is similar in size to the Milky Way, perhaps slightly larger. Andromeda contains perhaps 1 trillion stars compared to the Milky Way's 100 to 400 billion. Andromeda is often cited as slightly larger, but the difference is modest. They're comparable in scale. Most galaxies are much smaller than the Milky Way. The Magellanic Clouds, satellite galaxies of the Milky Way, contain only a few billion stars each. Dwarf galaxies, the most common galaxy type, contain millions to billions of stars, far fewer than giant galaxies. In terms of morphology, the Milky Way is a large spiral galaxy. Spiral galaxies like the Milky Way and Andromeda have disks with spiral arms and central bulges. Elliptical galaxies, another major type, lack disks and spiral arms. They're roughly ellipsoidal in shape. They typically contain older stars and less gas than spirals. Irregular galaxies lack regular structure, often due to gravitational disruption from nearby galaxies. Lenticular galaxies have disks and bulges like spirals, but lack prominent spiral arms. The morphological classification of galaxies, based on visual appearance, correlates with physical properties. Spirals tend to be younger with active star formation. Ellipticals are older, more quiescent. The Milky Way, as a large spiral, is an active star-forming galaxy. It's creating new stars at a modest rate, about 1 solar mass per year, comparable to Andromeda. When the Milky Way and Andromeda merge, the combined system will become an elliptical galaxy. The merger will disrupt both disks, triggering intense star formation, but eventually settling into an elliptical configuration. This transformation has been modeled in simulations. The merger simulations suggest the resulting elliptical galaxy would be one of the largest in the local universe, but not a true giant like IC1101. For most of human history, the Milky Way was a mystery. Ancient peoples noticed the bright band of light crossing the night sky, but didn't know what it was. Different cultures had different explanations. The Greeks called it Galaxia Kyklos, the Milky Circle. The word galaxy comes from this Greek term, applied to all large stellar systems only after astronomers realized the Milky Way was one among many. In the 17th century, Galileo's telescope revealed the Milky Way was made of countless stars, but the scale remained unknown. In the 18th century, William Herschel attempted to map the galaxy by counting stars in different directions. He constructed a model where the solar system was near the center of an elongated stellar distribution, the first three-dimensional model of the galaxy. Herschel's model was flawed because it didn't account for dust obscuration, but it was the first serious attempt to understand galactic structure. In the 19th century, astronomers refined the understanding, recognizing that the galaxy had a disk-like structure with the sun somewhere within it. But the galaxy's true extent and the sun's location remained unknown. Some astronomers thought the sun was near the galactic center. Others argued it was in the outer regions. In the early 20th century, this became the subject of the Great Debate, a dispute between astronomers about galactic structure. Some astronomers, like Harlow Shapley, argued the Milky Way was enormous, about 300,000 light-years across, with the sun far from the center. Others, like Heber Curtis, argued the Milky Way was smaller, with the sun near the center. Shapley used observations of globular clusters, measuring their distances through parallax and period luminosity relationships for variable stars, and found they formed a roughly spherical distribution centered not on the sun, but offset by thousands of light-years. This suggested the galaxy's center was in the direction of Sagittarius, offset from the sun. We now know Shapley was essentially correct, though his estimate of galactic size was somewhat too large. Curtis's position was overturned by Edwin Hubble's observations that resolved individual stars in nearby galaxies, establishing they were separate islands of stars, galaxies themselves, not nebulas within the Milky Way. This great debate was resolved not by choosing between positions, but by recognizing that both the galaxy and the universe were vastly larger than anyone had imagined. Modern observatories revolutionized our understanding of the Milky Way. The Gaia spacecraft, launched by the European Space Agency, has been the most transformative recent mission. Gaia measures precise positions and motions for over 1 billion stars, creating a three-dimensional map of stellar positions and velocities. Gaia data revealed the warping of the galactic disk, detected stellar streams from disrupted satellite galaxies, confirmed the spiral structure, and refined measurements of the galactic center's mass. Gravitational interactions with satellites trigger tidal heating and can modulate star formation. The impending collision with Andromeda was set in motion billions of years ago when the two galaxies were closer together and gravitationally attracted each other. Understanding why the Milky Way is the way it is requires understanding its environment and its interactions with other galaxies. Current estimates suggest the galaxy forms about 1 solar mass of new stars per year. This means over the galaxy's 13.6 billion year history, it's converted roughly 13 billion solar masses of gas into stars. For perspective, that's about 0.01% of the galaxy's total mass. Most of the galactic mass remains as dark matter and unconverted gas. The density wave theory of spiral arms explains why star formation concentrates in spiral arms. As gas clouds orbit through spiral arms, they experience compression from the density wave. The compression triggers gravitational instability. When a gas cloud becomes dense enough, the gravitational force exceeds the pressure support holding it apart. The cloud collapses. As it collapses, the cloud fragments, breaking apart into smaller clumps which fragment further. Eventually, clumps become dense and hot enough for hydrogen fusion to begin. The most massive fragments, and thus highest density, highest temperature centers, ignite first, becoming stars. The initial mass function, the distribution of stellar masses produced, follows a power law. For every one massive star, there are roughly 100 low-mass stars. This skewed distribution has implications. Massive stars are short-lived but energetic. Low-mass stars are long-lived but provide less energy output. The total energy output of a star population is often dominated by the small number of massive stars, despite the vast majority being low mass. Star clusters form from the gravitational collapse of gas clouds. A single large cloud can break into thousands of clumps, each forming a star. The gravitational binding of these newly formed stars, still embedded in surrounding gas and dust, keeps them in a cluster. However, as massive stars form and die, their supernovae release enormous energy. This energy heats the surrounding gas, often dispersing it. Once the gas is gone, there's nothing holding the cluster together. Stars drift apart, and the cluster dissolves into the galactic disk. Some young clusters remain bound long enough to become open clusters, gravitationally bound associations of thousands to hundreds of thousands of stars orbiting together. Over tens of millions of years, even open clusters dissolve as stellar escapes gradually reduce membership. This demonstrates that star clusters are transient. They form from gas, stars disperse the gas through feedback, and the cluster dissolves. The age structure of open clusters reveals the history of star formation. By finding many clusters of different ages, we trace how star formation has varied over time. The Milky Way is more than just our cosmic home. It's a laboratory for understanding how galaxies form, evolve, and transform. Because we're inside the Milky Way, we can study its structure in detail, impossible for distant galaxies. We can measure individual star properties, track stellar motions, map chemical abundances, and trace galactic dynamics with precision. This detailed knowledge of our galaxy constrains models of galaxy formation. When theorists create simulations of galaxy formation in cosmological contexts, they check whether their simulations produce galaxies like the Milky Way. Galaxies that form in simulations often don't match observations. The simulated galaxies might be too small, too large, contain too many stars, or have incorrect structure. Researchers debug these simulations by comparing to the Milky Way's properties. Over time, simulation capabilities improve, reproducing more of the Milky Way's features. This process of learning from the Milky Way improves our understanding of galaxies throughout the universe. The Milky Way also teaches us about stellar evolution. The ages and compositions of galactic stars reveal how stars evolve, how massive stars die in supernova, how low-mass stars gradually cool as white dwarfs. The abundance patterns of elements in galactic stars reveal nucleosynthesis processes, which reactions create which elements, in what conditions, with what products. This knowledge of stellar evolution applies to stars everywhere. By studying our galactic neighborhood, we understand stellar physics universally. The Milky Way demonstrates how planetary systems form. The abundance of planets in galactic surveys shows that planet formation is ubiquitous. It's the norm, not the exception. This suggests that habitable planets probably exist throughout the galaxy. If life formation is probable given habitable conditions, then life might be common in the Milky Way. Whether any extraterrestrial civilizations currently exist remains unknown. But the Milky Way's physical properties suggest the galaxy could harbor billions of potentially habitable worlds. The Milky Way also embodies the principle of cosmic insignificance. We're on a small planet orbiting a medium-sized star in an outer spiral arm of one galaxy among hundreds of billions. By cosmic standards, we're impossibly small, impossibly insignificant. Yet, from this insignificant vantage point, we've learned to understand the galaxy, to map its structure, to trace its history, to predict its future. We've learned the principles of physics that govern not just the Milky Way, but the entire universe. We're insignificant, yet we've achieved genuine understanding. I want to return to that moment, lying on my back on a camping trip, staring up at the Milky Way stretched across the night sky. I was 17. I didn't know all the things I've shared in this video. I didn't understand the spiral structure, the dark matter, the supermassive black hole at the center, the billions of planets orbiting billions of stars. But I felt something. I felt the scale. I felt the vastness. I felt the vertigo of realizing I was inside this vast structure, one person on one planet orbiting one star among billions. Years of learning didn't diminish that feeling. If anything, it deepened it. Now when I look at the Milky Way, I see more. I see the spiral arms, density waves compressing gas, triggering star formation. I see the central bulge and the dark matter halo extending beyond. I see dust clouds obscuring light and forming new stars. I see billions of stars, many with planets, some with life perhaps, all part of the same structure that contains me. I see the future, 4.5 billion years from now, when Andromeda collides with the Milky Way, transforming both into a new elliptical galaxy. I see the eventual fate of that merged galaxy, billions of years in the future, when star formation ceases and dead stellar remnants slowly evaporate or fall into black holes. Understanding these things doesn't make the Milky Way less wondrous. It makes it more so. Science often gets portrayed as diminishing wonder, as if learning how things work removes their mystery and beauty. But that's backwards. Learning how something works reveals depths you couldn't see before. The Milky Way isn't less wondrous because I understand spiral density waves. It's more wondrous because I can appreciate the elegant physics making those patterns possible. It's not less miraculous that we orbit a star that formed from gas, enriched by a previous generation of supernovae. It's more miraculous because I understand the cosmic chain that had to occur for us to exist. The vertigo I felt at 17 is still there, but it's informed by knowledge. It's deeper, more nuanced, more profound. When that 17-year-old me realized I was inside the Milky Way, I was experiencing awe. Now, with years of learning, I can still experience that awe, but I can also understand why the awe is warranted. The Milky Way is indeed vast, incomprehensibly large. It is indeed ancient, billions of years old. It is indeed full of wonders. Binary stars, supernovae, black holes, planets, stellar nurseries, stellar graveyards. And we're part of it. We're made from its materials. We orbit one of its stars. We're conscious observers within this vast structure, capable of understanding it. That's everything. That's what makes existence meaningful. When you look up at the night sky and see that bright band of light, the Milky Way, you're looking at home. Not Earth, though that's home too, but the galaxy itself, the vast structure that contains everything you've ever known. And somewhere in that vast structure, billions of years in the future, another collision, another transformation, another chapter of cosmic history. The Milky Way isn't static. It's alive with processes, stars forming and dying, galaxies colliding and merging, matter transforming, energy dispersing. It's dynamic, evolving, continuing. And right now, in this moment, you're a conscious part of it, capable of understanding it, capable of finding meaning in it. The Drake equation is a famous attempt to estimate the number of communicating civilizations in the Milky Way. Proposed by Frank Drake in 1961, the equation multiplies factors. Where R star is the rate of star formation in the galaxy, Fp is the fraction of stars with planets, Ne is the average number of habitable planets per star, Fl is the fraction where life emerges, Fi is the fraction where intelligent life evolves, Fc is the fraction that developed communication technology, L is the average lifetime of communicating civilizations. The problem is that most of these terms are unknown. We can estimate some. We now know Fp is close to 1. Nearly all stars have planets, and N80 might be substantial, multiple habitable zone planets per star. But Fl, Fi, Fc, and L remain almost completely unknown. If we're conservative and assume Fl, Fi, and Fc are each 1% and L is 10,000 years, the Drake equation gives roughly one communicating civilization in the galaxy at any time. This means we'd probably be alone now, but other civilizations might have existed or will exist at other times. If we're optimistic and assume these factors are higher, the Drake equation could suggest millions of communicating civilizations. The enormous range of possible answers reflects our ignorance about whether life is common or rare, whether intelligence typically evolves when life exists, whether technological civilizations typically destroy themselves or become long-lived. The Fermi paradox, the contradiction between the high probability of extraterrestrial civilizations and the lack of detected signals, depends critically on these unknown factors. One resolution: the great filter. If some step in the process from star formation to long-lived communicating civilization is extremely improbable, it could reduce the expected number of civilizations to zero, or very few. Is the great filter in our past, we're incredibly lucky to exist, or our future, something will destroy our civilization? If it's in our future, the Milky Way might contain countless dead civilizations, but no currently active ones besides us. This depressing possibility, that technological civilizations inevitably self-destruct, can't be ruled out, but it also can't be confirmed. We simply don't know whether civilizations are common, rare, or absent in the galaxy. The search for extraterrestrial intelligence continues. Perhaps a signal will arrive tomorrow. Perhaps we'll search forever and find nothing. The Milky Way remains a mystery regarding life beyond Earth. The exoplanet revolution has fundamentally changed how we think about the Milky Way. Before 1995, planets were theoretical. We suspected they orbited other stars based on formation theory, but we'd never observed one. In 1995, Michel Mayor and Didier Queloz detected a planet around 51 Pegasi using Doppler spectroscopy. This first exoplanet discovery was shocking. It was a massive planet orbiting very close to its star, completely different from Jupiter, which orbits far from the Sun. Hot Jupiters, as they're called, seem to violate what we thought we knew about planetary formation. Our theory said massive planets form far from stars where there's enough material, then might migrate inward. But we weren't sure migration actually happened. The discovery of hot Jupiters proved it could. This single exoplanet discovery revolutionized planetary science. We realized our solar system wasn't the model for all systems. Planetary systems could be radically different. The first Earth-sized exoplanet was discovered in 2009, Kepler 10b. This was significant because it showed Earth-sized planets could form, not just gas giants. But Kepler 10b orbits extremely close to its star, making its surface thousands of degrees Kelvin. It was far from habitable. The real breakthrough came with Kepler 22b in 2011, an Earth-sized planet in the habitable zone of a Sun-like star. It was the first potentially habitable exoplanet discovered. Since then, hundreds of habitable zone planets have been discovered. Kepler 452b, a particularly famous one, orbits a star remarkably similar to our Sun. The TESS mission, launched in 2018, is discovering thousands more exoplanet candidates. TESS observes nearly the entire sky, looking for the small brightness dips when planets transit their host stars. By observing so many stars, TESS is revealing the statistical properties of planetary populations. We're learning what fraction of stars have planets, how many planets typical systems have, how common Earth-sized planets are, how common habitable zone planets are. The picture emerging is that planets are ubiquitous. Most stars have them. Earth-sized planets are common, perhaps more common than gas giants. Habitable zone planets are probably common too, billions in the galaxy by some estimates. These discoveries suggest the conditions for life, a rocky planet in a star's habitable zone, are widespread in the Milky Way. Whether those conditions actually produce life remains unknown, but they're abundant enough that if life formation is likely given suitable conditions, the galaxy could harbor immense numbers of biospheres. The Milky Way is a book of cosmic history. If you know how to read it, you can trace the galaxy's entire story. The oldest stars in globular clusters tell us about the galaxy's infancy. These 13-billion-year-old population 2 stars show what chemical compositions were possible when the universe was young. The metal abundances increase from old stars to young stars, revealing how stellar nucleosynthesis enriched the interstellar medium over billions of years. The metallicity gradient from the galactic center outward tells us about the history of star formation. The center was most active early, enriching quickly. The outer disk enriched slowly. Stellar kinematics reveal different epochs of galactic assembly. Disk stars have low random velocities because the disk is young in cosmic terms and self-gravitating. Halo and bulge stars have high random velocities, evidence they were assembled by gravitational interactions billions of years ago. The stellar streams detected by Gaia are recent evidence of ongoing galactic cannibalism, satellite galaxies being torn apart by tidal forces. The warping of the galactic disk might result from a recent interaction with a satellite galaxy, gravity pulling the disk out of alignment. All these observations piece together a history of the Milky Way. It began as a collapsing cloud of gas in the early universe, perhaps 13 billion years ago. As it collapsed, the densest regions fragmented into stars. The most massive formed first, had brief lives, and exploded as supernovae, creating heavy elements. Over billions of years, successive generations of stars formed from progressively enriched gas. The galaxy grew through mergers with smaller galaxies, cannibalizing satellite systems and incorporating their stars. A disk structure assembled, probably through tidal interactions with other galaxies. The disk became a site of ongoing star formation. Spiral arms emerged, possibly driven by bar-like instabilities or density wave resonances. The supermassive black hole at the center grew, either formed with the galaxy or assembled by accretion and mergers. Billions of years of evolution produced the complex dynamic galaxy we observe today, and this history continues. The Milky Way today is still evolving, still forming stars, still occasionally cannibalizing satellite galaxies, still headed toward collision with Andromeda. Understanding this history is understanding our own origins. Every atom in your body was forged in stars. Those stars formed from gas enriched by previous stellar generations going back to the galaxy's infancy. You are made of stellar material assembled over billions of years of galactic evolution. You are a product of the Milky Way's history. The Milky Way is one of the most accessible cosmic objects. Unlike distant galaxies requiring telescopes, the Milky Way is visible to the naked eye from anywhere with reasonably dark skies. This accessibility makes it special. For most of human history, the Milky Way was the primary cosmic object people observed. The appearance of the Milky Way from Earth depends on your location and time of year. From the northern hemisphere, the brightest part is visible in summer and autumn. From the southern hemisphere, the best views are during southern winter. The brightest part of the visible Milky Way is in the direction of Sagittarius, toward the galactic center. This concentrated brightness results from looking toward the dense central bulge and the densely packed disk beyond. The dimmest parts of the visible Milky Way correspond to dust clouds obscuring starlight. In truly dark locations, far from city lights, thousands of stars are visible within the band of the Milky Way. The number is astonishing. Urban locations might show a few hundred stars in the Milky Way band. Pristine dark sky locations show tens of thousands. This difference illustrates how important light pollution is. The Milky Way is diminished by artificial lighting. Seeing it requires escaping to dark locations. Binoculars show incredible detail within the Milky Way band. Individual star clusters appear. Dust clouds become apparent. The complexity of the stellar distribution becomes obvious. Telescopes reveal even more. Individual stars, nebulae, clusters in profusion. Many famous deep sky objects lie along the Milky Way band. The Orion Nebula, M42, a bright star-forming region, the Pleiades, a young star cluster, the Crab Nebula, M1, remnant of a nearby supernova, the Ring Nebula, M57, Planetary Nebula, countless globular clusters. These objects are our local galactic neighborhood. Studying them reveals the processes that shape the galaxy. The best time and place to view the Milky Way is away from city lights, on a moonless night with clear skies. Observatories and planetariums often host viewing events where people can experience the Milky Way in optimized conditions. Photographing the Milky Way has become popular with astrophotography enthusiasts. Modern cameras capture detail invisible to the eye, revealing the full structure and extent of the galactic disk. These photos inspire wonder. They show objectively and visually that we live inside a vast structure of billions of stars. Throughout this exploration of the Milky Way, we've covered the physics, the structure, the history, the current state, and the future. We've learned that the Milky Way is vast, 100,000 light years across, containing hundreds of billions of stars. We've learned that it's ancient, 13 billion years old, formed near the beginning of cosmic history. We've learned that it's complex, organized into structures, disk, bulge, halo, spiral arms, with substructures, star clusters, stellar streams, remnant galaxies. We've learned that it's dynamic, constantly evolving, forming stars, cannibalizing satellites, rotating, warping, transforming. We've learned that it's home to the solar system, to Earth, to us. All of this knowledge is extraordinary. A century ago, we didn't know the sun was one star among billions in a galaxy. 2 centuries ago, we didn't know galaxies existed at all. The rapid accumulation of knowledge about the Milky Way represents one of humanity's greatest intellectual achievements. And this knowledge continues growing. Every year, new discoveries refine our understanding. Gaia continues observing, measuring stellar positions more precisely. TESS continues discovering exoplanets. Gravitational wave detectors discover colliding neutron stars. Radio telescopes map gas clouds. Infrared observatories reveal star formation. We're in an era of rapid advancement in galactic astronomy. What might we learn in the next decade? We might discover whether habitable zone planets truly can harbor life. We might detect signals from extraterrestrial civilizations. We might find evidence of black holes disrupting planetary systems. We might refine the merger prediction for Andromeda and Milky Way collision to understand its consequences better. We might discover entirely unexpected phenomena we haven't considered. The Milky Way remains full of mysteries. We understand its general structure and many details, but fundamental questions remain. What is dark matter? How do supermassive black holes form and evolve? How common is life in the galaxy? Are there technological civilizations? What is the galaxy's ultimate fate? These questions will drive research for decades. But beyond the scientific knowledge, the Milky Way offers something else: perspective. Understanding that you're on a small planet orbiting one star among billions in a galaxy, orbiting with hundreds of billions of other stars, can be humbling. It can diminish human concerns. What does a personal problem matter in a galaxy of that scale? But it can also inspire. You're conscious in a universe of that vast scale. You can understand it. You can contemplate it. You can find meaning in it. The Milky Way is your home. Not the only home. Earth is your home too, and your city, and your house. But cosmically, the Milky Way is your galactic home. Understanding it is understanding yourself, understanding where you come from, what you're made of, where you're going. Misconception 1. The Milky Way is unique. Reality. The Milky Way is a large spiral galaxy, but many similar galaxies exist. Andromeda is comparable in size. Thousands of galaxies have similar morphology and properties. Misconception 2. The Milky Way is the largest galaxy. Reality. The Milky Way is large, but C1101 and some other galaxies are vastly larger. The Milky Way is large, but not exceptional in size. Misconception 3. The Sun orbits around the galactic center quickly. Reality. The Sun takes 230 million years to complete one orbit. This is slow by any human measure. At our orbital velocity, it takes geological timescales to perceptibly change our position. Misconception 4. The Milky Way is stationary. Reality. The Milky Way orbits through space, interacts with other galaxies, has its structure distorted by gravitational interactions. Misconception 5. Planets are rare in the Milky Way. Reality. Recent exoplanet discoveries show planets are ubiquitous. Most stars probably have at least one planet. Misconception 6. The Milky Way's collision with Andromeda will destroy Earth. Reality. The collision will occur in 4.5 billion years. By then, the Sun will have killed Earth through natural stellar aging. Even during the collision, stars are so spaced that direct collisions are unlikely. Orbital disruptions are possible but not guaranteed for the solar system. Misconception 7. We can see the whole Milky Way from Earth. Reality. Dust obscures much of the galaxy. From Earth, we see mainly the visible disk, but not the full galactic structure. Radio and infrared observations are needed to see through dust. Misconception 8. Dark matter is a placeholder for unknown physics. Reality. Dark matter is necessary to explain observed galactic rotation curves and other phenomena. While we don't know what dark matter is, its existence is well supported. Misconception 9. The Milky Way formed all at once. Reality, the Milky Way, assembled gradually through mergers, accretion, and continuous star formation over billions of years. Misconception 10: extraterrestrial life would be silicon-based or made of exotic elements. Reality: we'd expect extraterrestrial life to be carbon-based like Earth life because carbon's chemistry is uniquely suited to complex molecules. But we can't rule out exotic alternatives. Correcting these misconceptions leads to more accurate understanding of our cosmic home. Neutron stars are among the densest objects imaginable. A teaspoon of neutron star material would weigh as much as Mount Everest. These remnants are held up by neutron degeneracy pressure, the quantum mechanical resistance of neutrons to being squeezed closer together. The most famous neutron star is the Crab pulsar, which rotates 30 times per second, emitting pulses of radiation like a lighthouse. Some pulsars rotate over 700 times per second, millisecond pulsars spinning so fast they're on the verge of being torn apart by centrifugal force. Black holes are objects where gravity is so intense that not even light escapes. The Milky Way probably contains millions of stellar black holes, created from massive star deaths. The accretion of matter around black holes creates some of the most energetic phenomena in the galaxy. Material spiraling inward reaches temperatures millions of degrees and emits intense X-rays. Supernova remnants are spectacular structures. The Crab Nebula, expanding at 1,500 kilometers per second, still shows the violent remnants of the explosion observed nearly 1,000 years ago. Young supernova remnants are hot, emitting in X-rays. As they age, they cool and fade, eventually merging with the interstellar medium. The youngest supernova remnant known is Cassiopeia A, with the explosion occurring roughly 300 years ago, though light from it reached Earth later. Wolf-Rayet stars are massive stars with extreme properties. They have lost their outer layers, exposing their hot cores, and are surrounded by dense shells of ejected material. These stars are visual manifestations of stellar evolution on their way to becoming supernovae. Binary systems with neutron stars or black holes are fascinating. Laboratories. Matter from the normal star is pulled toward the compact object, forming an accretion disk that heats and radiates. X-ray binaries are among the brightest X-ray sources in the galaxy. Gravitational waves have now been detected from merging neutron stars and black holes in the Milky Way and nearby galaxies. These gravitational waves carry information about the merger process and the final object created. The first gravitational wave detection, from LIGO in 2015, was from two black holes merging billions of years ago, but the signal traveled only recently. This demonstrates that galactic-scale gravitational events release detectable waves. The Milky Way is full of such remarkable objects and events. Each one represents extreme physics, conditions and properties found nowhere on Earth. Studying these objects teaches us about the limits of physics, the behavior of matter and gravity under extreme conditions. The James Webb Space Telescope, launched in 2021, is revolutionizing infrared astronomy. JWST can observe galaxies from the early universe and study star-forming regions throughout the Milky Way with unprecedented detail. JWST is already discovering young stars in dusty regions, observing exoplanet atmospheres to search for potential biosignatures, and revealing the chemistry of star-forming regions. These observations will continue for the next decade or more as JWST explores the infrared universe. The Nancy Grace Roman Space Telescope, launching in the mid 2020s, will provide ultraviolet and visible light observations complementing JAD's WST's infrared data. Roman will discover black holes in the Milky Way through microgravity lensing, observe exoplanet systems to better understand planetary formation, and trace the structure and chemical evolution of the galactic disk. Ground-based observatories are also advancing. The Vera Rubin Observatory's Legacy Survey of Space and Time will observe billions of objects, tracking how they change over time. This survey will detect supernova throughout the galaxy and beyond, track asteroid movements, discover new, potentially hazardous asteroids, and reveal the structure of the Milky Way. The next generation Very Large Array will improve radio observations, providing higher sensitivity and resolution. These missions will reveal new aspects of the Milky Way we haven't yet explored. We might discover new types of objects, exotic phenomena predicted by theory but never observed. We might find evidence of advanced civilizations, technosignatures indicating extraterrestrial technology. We might refine measurements of the Andromeda collision, predicting more precisely what will happen when the two galaxies merge. We might discover the nature of dark matter through observations of its gravitational effects. Most likely, we'll discover things we haven't anticipated. That's the nature of scientific research. We've explored the Milky Way from many angles: structure, history, current state, future, observations, implications. What does it all mean? The Milky Way is more than just a collection of stars. It's a complex system that has evolved over billions of years, shaped by gravity, stellar processes, and cosmic interactions. It's a system that produced conditions for life to emerge, at least on one planet orbiting one star. It's a system that continues evolving, continuing to form new stars, continuing to transform through stellar processes and galactic interactions. It's a system that will, in the distant future, merge with another galaxy, creating something new. The Milky Way embodies fundamental principles of physics: gravity, thermodynamics, quantum mechanics, applied at galactic scales. Understanding the Milky Way means understanding how these principles shape cosmic structures. It means understanding your own place in the universe, not at the center, but as a participant in a vast system. It means recognizing that you're made of material forged in ancient stars, assembled into a conscious being capable of understanding the galaxy itself. The Milky Way is home, but it's also a teacher. It teaches us humility. We're small in cosmic terms. It teaches us wonder. The structures and processes are magnificent. It teaches us connection. We're part of this system, intimately linked to stellar processes and galactic evolution. When you look up at the night sky and see the Milky Way stretching across the heavens, you're looking at Asa, home. You're looking at billions of suns. You're looking at countless worlds. You're looking at the vast structure within which you exist. The Milky Way teaches us that the universe is far more complex and interconnected than simple explanations suggest. When you learn that your body's iron atoms were forged in a supernova, that your oxygen was created in a massive star's core, that your calcium in your bones was scattered into space by a stellar explosion, you realize something profound. You're not separate from the cosmos. You're made of it. You're a particular arrangement of cosmic materials. This understanding profoundly changes perspective. You're not an observer viewing the universe from outside. You're a participant in it. You're the universe experiencing itself. The Milky Way demonstrates this connection. It created the conditions that led to life on Earth. It created the atoms that compose you. You are literally and not metaphorically made of star stuff. Carl Sagan expressed this eloquently. The atoms of our bodies are traceable to origins in the Big Bang, and the fact that we are here, that we exist, is because those atoms were captured billions of years ago in a supernova, so we are, quite literally, made of star stuff. This isn't poetic exaggeration. It's literal scientific fact. Understanding the Milky Way thus becomes understanding yourself at the deepest level. The complexity of the galaxy, its billions of stars, its countless structures, its dynamic processes, is matched by the complexity of consciousness arising from matter organized in particular ways. Consciousness is rare in the universe. Matter is common. Life might be common or rare, but consciousness, the ability to contemplate existence, might be extraordinarily rare. The Milky Way might contain only one conscious species, yes, or it might contain many. We don't know. But the fact that consciousness emerged at least once on Earth in the Milky Way suggests that under the right conditions, matter can organize in ways that produce awareness. This is one of the deepest mysteries science hasn't solved. How does matter become conscious? The Milky Way can't answer this question directly, but by revealing the conditions under which life emerges, by showing us the prevalence of habitable worlds, by demonstrating the universal applicability of physics, the Milky Way illuminates the question. Understanding the Milky Way is part of understanding consciousness itself. This is perhaps the greatest significance of studying our cosmic home. Through understanding the galaxy, we understand ourselves, our origins, our composition, our place in the cosmos, and our capacity to understand the very universe that created us. This circular understanding, the universe knowing itself through consciousness that emerged from its own structures, is the deepest achievement of human science. The Milky Way structure reveals fundamental principles about how galaxies form and evolve, principles that apply throughout the universe. The disk structure, flat, rotating with concentrated stellar populations, emerges when a system reaches gravitational equilibrium with angular momentum. Gas clouds collapsing under gravity form disk-like structures because angular momentum must be conserved. As material falls inward, it spins faster, like a spinning ice skater pulling in their arms, and settles into a disk. This principle explains why galaxies so often have disk structures. It's not specific to the Milky Way, it's a consequence of fundamental physics. The spiral arms similarly emerge from fundamental processes. The density wave pattern that creates spiral arms is a self-sustaining structure maintained by the collective gravity of stars and gas. The spiral pattern rotates slower than stellar orbits at most radii, creating a corrotation radius where pattern and stellar speeds match. This corrotation radius appears special. It's often where star formation is particularly active, suggesting dynamical resonances enhance star formation there. Understanding spiral arms teaches us about structure formation in self-gravitating systems, knowledge applicable to many cosmic phenomena. The central bulge and black hole present another fundamental principle. Massive systems naturally develop supermassive black holes at their centers. Virtually all large galaxies appear to have supermassive black holes. The mass of the central black hole correlates with the mass of the galaxy, a relationship discovered by correlating Sagittarius A star's mass with the Milky Way's bulk properties. This correlation is mysterious. It suggests a deep connection between black hole growth and galaxy development. but the exact cause remains unclear. Understanding this relationship is one of the active frontiers of galactic astronomy. The halo and dark matter represent perhaps the deepest mystery. Dark matter comprises most of the galaxy's mass, yet we don't know what it is. Current observations can't definitively distinguish between different dark matter candidates. The particle nature of dark matter remains unknown. Future observations might detect dark matter particles or might reveal it's something entirely unexpected. The mysteries in the Milky Way's structure reflect the frontiers of physics itself. By understanding these mysteries, we probe the limits of current physics and seek the new principles that might lie beyond. This is the power of studying our cosmic home. It connects us to the deepest questions of physics and cosmology. We stand at an exciting moment in galactic astronomy. The tools to observe the Milky Way have become extraordinarily powerful, and new instruments promise to revolutionize our understanding. Gaia has transformed our knowledge by providing precise positions and motions for over 1 billion stars. Future Gaia releases will provide even more data, revealing finer structure and enabling better parallax measurements to distant objects. The combination of Gaia's astrometry with other surveys, spectroscopic data from missions like SDSS, and radial velocities from various observers, creates a complete three-dimensional map of the Milky Way and its motions. This map reveals the history written in stellar kinematics. By understanding how stars move, we can infer the forces that shaped those motions. We can trace back the orbits to understand the galaxy's history. The detection of stellar streams, thin filaments of stars tracing disrupted satellite galaxies, is providing evidence of ongoing galactic cannibalism. As we detect more streams and characterize them better, we learn about the galaxy's recent interactions and build a dynamic picture of galactic assembly. The discovery of exoplanets has transformed our understanding of planetary systems. Finding that planets are ubiquitous, most stars have at least one planet, suggests the Milky Way is full of worlds. If some fraction of those worlds harbor life, the galaxy could be teeming with biology. Detecting even one example of extraterrestrial life would be transformative. It would confirm that life emerges naturally wherever conditions permit. The SETI efforts continue, listening for signals from technological civilizations. If we detect a signal, it would confirm intelligent civilizations exist. If we don't detect anything despite vast improvements in detection capabilities, it might suggest technological civilizations are rare or short-lived. Either outcome would be scientifically profound. The study of the Milky Way ultimately tells us about ourselves. We are conscious observers within this vast system, capable of understanding the principles governing its structure and evolution. This achievement, consciousness arising from matter and achieving understanding of the universe from which it emerged, is perhaps the most remarkable phenomenon in the cosmos. The Milky Way isn't just our home, it's the context for existence itself. Understanding it is understanding the deepest questions of origin, structure, and meaning. This is why the Milky Way matters. This is why studying it deserves our effort and resources. Through the ages, humans have looked up at the night sky and seen the Milky Way. Different cultures gave it different names, but all recognized its significance. The Milky Way has been a constant in human consciousness, a visible reminder that we live within something vast and beautiful. In ancient times, when most people lived under dark skies, the Milky Way's appearance was striking. The bright band of light stretching across the heavens inspired wonder, mythology, and contemplation. Different cultures interpreted the Milky Way differently. Some saw it as a river of light, others as the path of souls, some as the body of a deity. These mythological interpretations, while not scientifically accurate, captured an essential truth. The Milky Way is significant, it's worthy of contemplation and wonder. Modern science has refined our understanding but hasn't diminished the wonder. If anything, understanding the physics behind the Milky Way deepens our appreciation. We now know the Milky Way isn't a river or a deity, but something far more remarkable, a vast system of billions of stars, formed from the remains of earlier stars, governed by gravity and thermodynamics, home to countless worlds, possibly harboring life. This scientific understanding is profound precisely because it's based on evidence and reason. We don't just imagine the Milky Way. We observe it, measure it, understand its properties and dynamics. The Milky Way embodies principles that apply throughout the universe. By understanding our galaxy, we understand galaxies billions of light years away. By understanding our local cosmic neighborhood, we understand the cosmos itself. The Milky Way connects us to the universe. It connects us to ancient stars whose remnants comprise our bodies. It connects us to future generations who will live in the merged remnant of the Milky Way in Andromeda. It connects us to the possibility of life elsewhere. Billions of potentially habitable worlds orbiting billions of stars. The Milky Way is home, teacher, and profound mystery all at once. When you look up at the night sky and see the Milky Way stretching across the heavens, you're looking at something that has captivated humans for millennia, something that science continues to reveal new mysteries about, something that connects you to the cosmic story of which you're a part. Our solar system's location within the Milky Way isn't random. The position in the outer spiral arm between major density waves in a relative quiescence region. These factors likely enabled life to develop on Earth. Had we been in a major spiral arm, we would have been exposed to more intense radiation from young, massive stars. This would have made the surface hostile to life for most of Earth's history. Had we been closer to the galactic center, we would experience more disruptions from stellar encounters and supernovae. Planetary orbits would be destabilized more frequently, making planetary system stability rare. Had we been farther out in the halo, we would have formed in metal-poor gas, heavy elements more recent than far outer regions, making planetary formation less likely. Planets require heavy elements to form. Our location in the disk, but in a relatively quiet region with sufficient heavy elements, is ideal for planetary system formation and the stability required for life to develop. This isn't unique. Other locations in the Milky Way probably have similar properties. The galaxy likely contains billions of planets with similar conditions to Earth. But our specific location allowed consciousness to emerge on Earth. From this small world, orbiting one star in an outer spiral arm of one galaxy among hundreds of billions, humans became aware of the universe. This is remarkable. Against odds that should make it vanishingly unlikely, matter organized into patterns capable of contemplating existence. That contemplation, that self-awareness, is the most remarkable phenomenon we know. The Milky Way produced the conditions for this to occur. The galaxy's billions of stars created opportunities for worlds to form. One of those worlds became home to life. That life evolved consciousness. Consciousness then turned its awareness back on the galaxy that created it, seeking to understand its structure and origins. This circular understanding, the universe understanding itself, is perhaps the deepest achievement possible. When you recognize that you are the universe becoming conscious of itself, When you realize that your contemplation of the Milky Way is the galaxy contemplating its own existence, something shifts in your perspective. You're not separate from the cosmos. You're the cosmos experiencing itself from within. The Milky Way is not just external reality to be observed, it's part of what you are. This realization that subject and object, observer and observed, are ultimately unified is perhaps what science at its deepest level reveals. The Milky Way isn't just our home, it's us. We are the Milky Way made conscious. The story of the Milky Way is our story. It's the story of how the universe produced conscious beings capable of understanding it. Every atom in your body tells that story. The iron came from supernova explosions billions of years ago. The oxygen formed in massive star cores. The carbon, nitrogen, phosphorus, all essential for life, were created in stars and scattered into space. That scattered stellar material eventually accumulated into Earth. Life emerged from that material. Consciousness emerged from that life. Now, billions of years later, consciousness contemplates the galaxy from which it arose. This is the deepest meaning of understanding the Milky Way. It's not just intellectual knowledge of distances and masses and structures. It's existential knowledge. Understanding that you are part of an unbroken chain of cosmic history stretching back to the Big Bang. When you look at the Milky Way, you're looking at your origin. You're looking at the process that created you. That realization is transformative. It changes how you see yourself, your place in the universe, your relationship to all other life. The Milky Way connects us to everything, to every star, every planet, every possible world where life might exist, to every conscious being that might have emerged elsewhere, to the past billions of years of stellar and galactic evolution, to the future billions of years when the galaxy will transform through collision and merger. The Milky Way contains multitudes. It contains the potential for countless worlds, countless civilizations, countless forms of consciousness, yet all of it, every atom, every star, every thought, is unified in one grand cosmic system governed by gravity and the laws of physics. To understand the Milky Way is to understand yourself. To appreciate it is to appreciate the miracle of existence. The next time you look up at the night sky and see that bright band of light, the Milky Way, remember that you're looking at home. Remember that you're made of it. Remember that contemplating it is the most profound achievement consciousness can accomplish. You are star stuff. You are the universe knowing itself. The Milky Way is your cosmic home, your origin, your connection to everything. Contemplate that, appreciate that, live with that understanding. Our cosmic address is the solar system, the local arm, Orion arm, the Milky Way galaxy, the local group, the Virgo supercluster. Each of these is a layer of cosmic structure, each nested within the next, creating a hierarchy of organization from our small planet to the largest structures we can observe. But this address, this location, tells a story. It tells where we are in space, but it also tells something deeper. It connects us to billions of other worlds, to countless stars, to the vast system of the Milky Way. Our address in the galaxy places us in the outer regions, between major spiral arms, in a region of relative stability and moderate metal abundance. It places us close enough to the galactic center to benefit from galactic chemical evolution. We have heavy elements, but far enough away to avoid the radiation environment that would sterilize planets. This location is ideal for life. It may not be unique. The Milky Way probably contains billions of equally suitable locations. but it's our location. It's where life emerged on Earth. The significance of our cosmic address is that it represents the meeting point of probability and cosmic history. Against vast odds at this location, consciousness emerged. Your existence depends on a chain of events stretching billions of years back. Had the Milky Way formed slightly differently, had our sun formed in a different location, had Earth emerged under different conditions, you would not exist. This doesn't diminish your significance. If anything, it enhances it. You are the improbable outcome of billions of years of cosmic history. You are significant precisely because existence against such odds is remarkable. The Milky Way reminds us of this every time we look up at the night sky. It reminds us that we are here, conscious, aware, capable of understanding the very galaxy that created us. That's the true significance of the Milky Way, not just as a structure of billions of stars, but as the context for consciousness itself. The Milky Way doesn't exist in isolation. It constantly interacts gravitationally with nearby galaxies, and these interactions shape its structure and evolution. Satellite galaxies, smaller galaxies orbiting the Milky Way, experience tidal forces from the larger galaxy's gravity. These tidal forces stretch and distort the satellite galaxies, eventually tearing them apart. The Large Magellanic Cloud and Small Magellanic Cloud are satellite galaxies being gradually disrupted by tidal forces. Both are slowly losing stars to the Milky Way's gravity. The Sagittarius Dwarf Elliptical Galaxy is perhaps the best example of galactic tidal disruption in action. This galaxy is currently being torn apart by the Milky Way's gravity. Its stars are being stripped away, forming long streams that wrap around the Milky Way multiple times. These stellar streams are visible through careful astronomical surveys. They trace out the path of the disrupted galaxy as it spirals into the Milky Way. Eventually, after billions of years, the Sagittarius dwarf's remaining core will be absorbed into the Milky Way's bulge or halo. Its stars will be incorporated into the larger galaxy. The Sagittarius dwarf will cease to exist as an independent system. This is the fate of all satellite galaxies eventually. The Milky Way is slowly cannibalizing its smaller neighbors, absorbing them, incorporating their stars and material into itself. This process has been occurring throughout the galaxy's history. The Milky Way's current large size partly results from merging with smaller galaxies over billions of years. The gravitational interactions also affect the Milky Way itself. Tidal forces from satellite galaxies can perturb the Milky Way's disk, causing warping or other distortions. The observed warping of the galactic disk, the fact that the outer regions bend upward and downward out of the galactic plane, might result from gravitational interactions with satellite galaxies. Computer simulations of galactic interactions show how tidal forces can warp and distort disks. The simulations match observed warping patterns, suggesting this mechanism explains the Milky Way's current structure. The impending collision with Andromeda will involve extreme tidal interactions. Both galaxies will exert powerful gravitational forces on each other, distorting both systems. The collision will unfold over hundreds of millions of years, with multiple passages as the galaxies orbit each other and gradually merge. During these passages, stars will be flung into new orbits. Some will be ejected from the galaxy entirely. Others will spiral toward the center. The disks will be disrupted and reformed. The final merger will produce an elliptical galaxy, a system very different from either of the original spiral galaxies. Understanding tidal interactions and galactic mergers is crucial to understanding galactic evolution. Most large galaxies have experienced mergers in their past. Most have satellite galaxies being disrupted around them. The universe is dynamic. Galaxies interact, collide, merge, transform. This dynamism shapes galactic structure and evolution on billion-year timescales. The Milky Way's influence on Earth extends beyond providing the stellar material that created our world. The galaxy's structure and dynamics actually affect Earth's climate and life over millions of years. Our solar system's orbit within the Milky Way brings us through regions of varying density. When the solar system passes through denser regions of the interstellar medium, the increased dust and gas around us affects Earth's climate. More dust and gas in the interstellar medium means more shielding from cosmic rays, but it also means more dust entering Earth's atmosphere. Increased atmospheric dust reduces solar input, potentially triggering ice ages. Conversely, when the solar system passes through less dense regions, cosmic rays increase and atmospheric dust decreases. These changes can warm or cool Earth's climate. The timescale of these galactic climate variations is hundreds of millions of years. Glacial periods and ice ages have timescales of millions of years. Galactic passages thus operate on similar timescales to major climate events in Earth's history. Some researchers have proposed correlations between Earth's extinction events and the solar system's position in its galactic orbit. The idea is that certain orbital positions, such as passage through the galactic plane, coincide with increased cosmic ray flux or other environmental stresses that trigger extinctions. This hypothesis remains debated, but it highlights an important principle. The Milky Way isn't just the distant background of Earth's existence. It actively influences conditions on our planet. The Sun's vertical oscillations as it orbits the galactic center occur with a period of roughly 100 million years. Some researchers have proposed this period matches extinction pulses seen in the fossil record, suggesting galactic cycles drive extinction events. Again, this remains speculative, but the fact that galactic scale processes might affect life on Earth demonstrates the deep interconnection between cosmic and terrestrial scales. On even longer timescales, the Milky Way's evolution affects what planets can support life. Early in the galaxy's history, when metal abundances were low, planets were probably rare or absent. As the galaxy enriched itself with heavy elements through stellar nucleosynthesis, planet formation became possible. Earth's existence depends on forming at a time when the galaxy had accumulated enough heavy elements. This was only possible after billions of years of stellar evolution. The Milky Way's history is thus Earth's history. The galaxy's chemical evolution made our planet possible. The galaxy's dynamics influence our climate. The galaxy's structure provides the context for life. We are not separate from the galaxy. We are embedded within it, shaped by it, dependent on it at every level. Looking up at the Milky Way from Earth, we see a galactic structure containing billions of stars, countless worlds, and the deep history of cosmic evolution. We see our home, not just the planet Earth, but the galaxy itself, the vast system that created us, sustains us, and will eventually transform us. That 17-year-old on a camping trip, overwhelmed by the sight of the Milky Way, was experiencing something profound. He was recognizing at an emotional level something that science confirms. He was part of this vast system. He was a conscious observer emerging from matter organized in particular ways, contemplating the very galaxy from which he arose. That experience, that recognition of connection and scale, is available to anyone who takes time to look up at the night sky away from city lights. The Milky Way is there, waiting to be contemplated, waiting to remind us of our place in the cosmos, waiting to inspire wonder and understanding. When you look at it, you're looking at billions of suns. You're looking at countless worlds. You're looking at the context for existence itself. The Milky Way awaits your contemplation. Look up, understand, wonder. The Milky Way is waiting. It has been waiting since its formation 13.6 billion years ago. It will continue existing for trillions of years more. It will eventually transform through collision and merge. It will eventually fade as stars die and are no longer replenished. But in this moment, in this era of cosmic history, it exists in a state where stars actively form, where planets orbit those stars, where life has emerged at least once, where consciousness has developed. This is the extraordinary moment we inhabit. This is the remarkable era we are part of. The Milky Way in this moment is alive with processes and possibilities. That's worth appreciating. That's worth understanding. That's worth contemplating. When you look up at the night sky and see the Milky Way, remember, you're looking at home. You're looking at the product of billions of years of cosmic history. You're looking at the context for existence itself. That's everything. Thanks for watching.